Welcome, Mechanics of Materials students. This is our third lecture in torsion of circular shafts. So far we have defined strain and stress relationships for a shaft that's being twisted. So this is subject to very particular conditions of displacement, namely small angles of twist, such that we can assume the only strain we have is shear in the z theta. That allows us to write super simple expressions relating applied moment, shear stress at maximum and at any point along the radius of the shaft, the moment of inertia of our shaft, polar moment, so moment with respect to the shaft axis, and our shear modulus G. So we're going to kind of take this another step further and look at another one of our elastic characteristics, which is strain energy. So if you remember back from your elasticity studies, we define strain energy as 1/2 of basically the products of stresses and strains in every direction, normal and shear, and we add that up over the entire volume of whatever we're looking at. So the bigger the volume, the bigger the strain energy, and sometimes we denote strain energy per unit volume and then integrate that around because it may change from location to location. Well, if we apply this expression to our twisted circular shaft, we got to remember that we could, let's start by remembering we can write XX, epsilon XX, epsilon YY. We can substitute R's and thetas and Z's for X's, Y's, and Z's. So if we were to do that and just kind of assume that, say, this sigma XX epsilon XX is like sigma RR epsilon RR, we know that the normal strains are all zero for our torsional shaft. So these first three terms go away. And we also know that all but one of the shear strains is zero, which means all but one of our shear expressions go away. So it turns out the only product of stress and strain that would go into our summation for our strain energy is just the tau z theta times gamma z theta. So our shear stress in the z theta direction times our shear engineering shear strain in the z theta. So our entire expression up here just is a single term. And we can make that even simpler by remembering that our engineering shear strain in the z theta, of course, is our shear stress divided by our modulus. So we can write everything in terms of just the shear stress in the z theta, and we end up with a 1 over our shear modulus out front. Integrate over whatever volume you want. As long as you have a continuous expression for your shear stress as a function of your the components of your volume, you can just integrate and get the total strain energy over whatever volume you care about. So let's look at different situations where we can actually execute that integral. So first of all, we're going to assume, again, isotropic, homogeneous material, so G is constant, so it can stay outside of the integral. We don't have to integrate it over the volume the way we would with a non-homogeneous material. And we're going to use our expression that we derived earlier for shear stress in the z theta relating to R, the radius of our circular shaft, and the applied moment to the shaft and the polar moment of inertia of our shaft. So we're just going to plop that right in for tau z theta, and it gets squared. Okay. Well, for a cylinder, we can define the volume as dA, meaning some element of the cross-sectional area, and dz. So we can integrate and add up all the area on a cross-section and then add up all of that up along all of the length. So dV is dA dz. And if we write volume that way, we will end up with an R squared and a dA dz. And we can take parts of that out and remember, okay, wait a minute, IZZ is R squared dA. So we have the potential to do some mathematical wrangling and maybe simplify this expression into something that's a lot easier to integrate. So we're going to go ahead and do that. So we're going to take one IZZ out of our squared denominator and write it like that. So this is kind of d-I-z-z. And then we're just going to leave our applied moment alone. It's being squared. And we're going to end up taking our r squared and then multiply by dv in the form of dA dz. So we now look at this and go, okay, hey, I have an r squared dA in both the numerator and the denominator, so I can get rid of both of those. And I'm left with my applied moment squared, one polar moment of inertia in the denominator, not IZZ squared, just IZZ, and now I'm only integrating along the length. If my moment doesn't change and my shaft area, or shaft radius more importantly, doesn't change, which will make a change in the shaft area, then these two are constant. Or if they change, all I have to do is do a piecewise integral and integrate along the length over the portions where they're constant, or for which I have an expression. So we're going to do exactly that. So we got a shaft, and this is an example of how you actually would take torque off of a drive shaft. So we have a shaft that extends from points C through B and A, and maybe further on. It's being supported in some bearings. It doesn't weigh very much, so we don't have to worry about flexural moment. But we're going to apply a moment at C, what looks like in the clockwise direction, so we're driving it there. Then we're going to apply counter moments at B and A, and those represents something that's being driven by the shaft. So we're kind of harvesting that moment at 2 points. We impart moment to the shaft at C, and then we take it off at B and A. So if we look at our moment distribution along the shaft, if we go from 0, we get a big step up in moment that we've applied. We were told we're applying a torque of 11.2 kilonewton meters. So we have this big step up, and it stays constant until we hit B, and then we have a step down because we're told that we are going to extract that torque evenly at points B and A. So we take half of it away. So from B to A, the shaft is only carrying 5.7 kilonewton meters of torque, and then it drops to 0 beyond A. So we could look at strain energy and anything else we cared about, twist, rate angle of twist, shear strain, shear stress, being appropriate to each of these areas. We've got an area C to B where we kind of have moment 1, and B to A where we have moment 2. The shaft modulus, shear modulus hasn't changed, shaft diameter hasn't changed, so that means the moment of inertia hasn't changed. So the only thing that's changing is our applied moment, and it's constant over those portions. So we can do a piecewise integral to get our strain energy and everything else we care about in this shaft by just basically adding up what's going on C to B and B to A, or if we care about maybe a maximum condition, we can look at which portion of the shaft that would be achieved in. I'm kind of looking at C to B as probably being if we're going to get maxima in shear stress, for instance, I would be concerned about it in here. So let's take a look. We're given a shaft radius of 50 times 10 to the minus third meters, and from that we can get our IZZ. And so now we're going to use our expressions that we've pre-derived for shear stress. And remember, our tau max is going to be out on that outer radius of the shaft, and it's going to occur where we've got a max in applied moment, which is between C and B. So we use our pre-derived expression for tau max, our R max times our applied moment divided by our moment of inertia, and we get 58 megapascals, which is probably well below the shear yield of most materials, definitely steel, but that's something you can check, see what kind of safety factor you needed. If we didn't encounter a tau max with the radius of the shaft in the area where we have the maximum of the larger applied moment, it's certainly not going to be too big between B and A. So we've tested the limiting case with just application of one equation. But angle of twist is cumulative. So if we were concerned with the angle of twist being too big, maybe out here beyond point A, we'd need it to add up the twisting cumulative between B and C, and then the twisting we get between B and A. So we're not going to get as much twisting imparted between B and A first, because the lower moment, all other things being considered, means our twist rate is less. It's also shorter. But we still need to know what it all ends up being in case we have a limit for the end of the shaft. So we're going to use our pre-derived integral over Z to get our twist angle. So now we're integrating our d phi from the start at a phi corresponding to Z equals 0, which is like 0 twist, over at point C where there's no length to have twisted through. And we're going to integrate to point B, which is 3 meters in length down the shaft. And to do that, we end up just using our pre-integrated expression, because moment doesn't change with Z, shear modulus doesn't change with Z, and moment of inertia doesn't change with Z. We haven't stepped up or down the shaft radius. If so, we could have just made another piecewise integral. So we're going to integrate angle of twist to the 3 meter mark using our high moment that we encounter between C and B, and we get 4.41 times 10 to the minus 2 radians. And then we're going to add the angle of twist that we get from B to A. So for that, we've got a lower moment. We've got the 5.7. We've got a shorter length, only 2 meters, but we have the same modulus and polar moment of inertia. And that ends up being 1.47 times 10 to the minus 2 radians. We add that to our 4.1 for a total twist angle over our 5 meter length of shaft of 5.88 times 10 to the minus 2 radians. Not 10 to the 2, it hasn't gone around several times. So that's a great example of how we would use a stepwise integral to denote what's happening over different regions where things are the same within a given region. If we, say, had, I don't know, some kind of fluid torque transfer, that we could say that for every unit length along this shaft, maybe we have some little paddles on it or whatever, we could say we are continuously withdrawing torque at blah 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 Newton meters per unit shaft length, then we would just integrate that as the moment we're taking away, and this graph would maybe have some kind of slope to it. No problem. As long as we have a continuous function for m or for our radius, in terms of Z, all we have to do to get twist angle is just to integrate those expressions. Okay. We can also, since we derived an expression for strain energy and haven't used it yet, we can go ahead and get the strain energy in each of those sections. So we can use an expression that we just derived up here of our tau squared for a cylindrical shaft, using our strain energy as 1/2 times our shear strain times our shear stress, integrated over our volume. We derive this expression, so we can deploy it, and so we can get strain energy for each of these appropriate sections. So we can use that, again pulling our 1 over shear modulus out of the integral. We can get the the strain energy, which in this case is of course all due to shear, from 0 to 3 meters, our high moment area, using moment squared over moment of polar moment of inertia, integrate over the full 3 meters. I get 251 joules. We can do the same thing for that lower moment end of the shaft, which is also smaller length. And because we're talking total strain energy, volume counts, length counts. So the B to A strain energy is less, both because we have a lower moment, and this time the moment's squared, so it counts like triple. The length is lower too, so that's why we've got such a small number for the strain energy in the B to A portion of the shaft than the C to B. Okay, Why would we care about strain energy if we already know shear stress, which we can relate to maybe a yield stress, and we know angle of twist, we know our applied moment and distribution? What would we do with that strain energy? Generally speaking, remember that elastic strain energy is one of the indicators of the potential to drive cracks. It is the crack driving energy. So if we were looking for inputs into a fracture mechanics model, say we're going to do a J integral or a Griffith theory fracture prediction, if we knew that the shaft maybe had some pre-existing flaws that were oriented such that they would be opened with the existing stresses. Now, nice thing, we only have shear stresses, which don't tend to favor crack opening as much as like tensile opening stresses, but they still can propagate cracks. So generally we would use this strain energy as a basis for fracture. You know, if there's a crack in there, we can use the strain energy as a way to say, hey, will it propagate? So generally speaking, in the case of the shaft, we'd kind of hope that if we had a big pre-existing flaw, that it was down in that B to A area where our strain energy was much less. So, and in fact, if you had the shaft and you knew there was a big crack somewhere in it, and you said, hey, do we want to flip the shaft around so the crack is in this part of the shaft or in this part of the shaft, you'd say, oh, you want it in the B to A portion. Ideally, it would be in the A and beyond portion where there's no stress at all. But that might be an application for strain energy. You wouldn't necessarily use that number directly, but it would be an indicator going forward. Okay, we're going to pick up one last topic. This is something that we'll get again with column buckling in what will probably be the final section of your study of mechanics of materials, but this is a little look ahead towards it because a column sometimes will be subject to twisting loads. And columns will buckle under compressive loads. Torsional shafts, if they are thin-walled cylinders, can also buckle when we twist them. If you get a thin aluminum can and twist it, you can see it doing that. Why would we be looking at a thin-wall cylinder in torsion? Because it's got a bigger moment of inertia for a given amount of volume in a cross-section area. So if you're lightweighting something, you're restricted to a certain material, so your shear modulus for the material is fixed. You can get more torsional stiffness, quote unquote, bang for your buck by distributing that area out in a ring. And the larger, thinner the ring, the bigger the polar moment of inertia and the stiffer you get. What's the limit? Torsional buckling. And at a certain point is a certain critical applied torsional stress. So our tau, our shear stress, so our tau z theta, there's going to be a point where rather than exceeding a shear yield for the material, you might buckle the shaft, you might crumple it, basically. So this is another one of those limits to check, and it's determined more or less empirically, and we can use all of that test data to come up with an expression for the maximum shear stress. So of course we're gonna be measuring that probably out on the outer radius, where we would have to worry about the shaft, a tubular shaft crumpling or buckling as we twist it. So let's see what we've got here. This is all empirical, so we're not deriving this from our model the way we did the shear stress that corresponds to like a given twisting rate. So we're saying that our critical shear stress, the one we do not want to exceed, is going to be a function of the square of our wall thickness per unit length ratio. So so the thicker we make it, the less, the higher a stress we can apply, but the longer we make it, the less stress we can apply, and they're squared terms. So they count double, so to speak. Then we've got some constants. So we've got, pi, which is a geometric factor. We got a couple of elastic constants. We've got our Young's modulus. So the stiffer a material is in tension, the higher tau is, but it's only linear. And we have 1 minus the Poisson's ratio squared. So that's, that's kind of looking closer to, kind of similar to our expression, our relationship between shear and tensile modulus, not quite the same. So basically, the stiffer a material is in tension, the more shear stress we can apply without buckling. And then we've got this factor K, which is sort of, I call it like a super geometric factor. And it's called the buckling coefficient. This is something you're going to look up. It's in terms of another coefficient, Z. This is coming out of one mechanics of material text. There may be other expressions for buckling coefficients, but this is one that has a fair bit of empirical data that goes with it. Generally, if you see something in a textbook, rule of thumb, it's pretty tried and true. If you see something in a research paper or something, it may only have a little bit of data. So if things end up in handbooks, and certainly anything for you folks going into civil, if it has ended up in statutes or code, first, it's probably legally required that you use it, and second, it's probably got a lot of empirical test data behind it. So those are fairly safe collections of data and expressions to use. So we'll assume this one's in that case. So our K over here, which is linearly related to our maximum critical amount of shear stress we can apply, is equal to 0.85 times some Z factor raised to the 3/4, and Z is now a function of length divided by the radius of the shaft times length divided by the thickness of the shaft. So now you can see the shaft geometry is involved at many points in this expression through both K and our prefix expression. And then again we have the Poissons showing up again. So we could probably ditch a lot of this other stuff and just write things just simply in terms of LRT, Poisson's ratio, and our elastic modulus. So the takeaway here is your actual applied shear stress is going to be limited by our yield stress, and then by this big old concatenation of elastic constants and geometric factors which define buckling onset, torsional buckling. So if you've got a real thin shaft, your tau critical for buckling may be way less than your tau for yield. And you, of course, must design for the smaller one. Otherwise, your shaft is going to crinkle and you won't have a good day. So if you're designing a shaft, basically you're going to be looking at what twist rate do I want, what total twist do I want, what maximum shear stress do I want to tolerate, and I'm going to base that on a buckling and a yield criteria with safety factor, whichever one is smaller. And then I can relate that to how big of a shaft do I need, what moment of inertia do I need, and what moment can I apply or do I want to apply. So we have a lot of knobs we can turn for designing. And of course, the one sad fact is when we look at our buckling criteria, we notice that unfortunately the things that will give us a big moment of inertia that will make the shaft stiffer torsionally, unfortunately will tend to make it more prone to buckling. So our deflection criteria, which is favored by a big moment of inertia, which is a real thin tube with a big radius, makes you more prone to buckling. So those are kind of the trade-off points that will kind of give you a design envelope that is bounded when we're looking at our shape. So, and of course, on the nice side, stiffer materials, bigger G's, bigger E's, are going to be in your favor, both from a buckling and a max deflection standpoint. So that is it for our torsional shafts, torsional circular shafts lecture series. We have restricted ourselves to circular cross sections just because it makes the integration easier of the relationship between moments of inertia and things like max stress. You can take the same argument and apply it to any cross-sectional shape. You would just need to use expressions that relate any time you're relating radius and you're calculating areas and volumes. You'd need to use appropriate geometric expressions to get material at a given distance from your radius for that shape. So you can use an ellipse or a square cross section. It's okay. You just need to use all of the factors that would or the expressions appropriate to that. So your moment of a polar moment of inertia would change, and all your radius area expressions would change, since you're looking at those different shapes. But otherwise, the same concepts will apply. So if you're even if you don't want to go through the full calculations, you can imagine how things like polar moments of inertia and average radii might change for a different shape, and at least get an idea of what if I went away from a circular cross section, what would that be, what effect would that have on my design. You can think through that using the same types of relationships that we've had and used to derive our circular. So, hope you have fun designing torsional shafts.